Hi listeners, welcome to the video lecture series on power electronics. In this video, we are going to derive the step up and step up down chopper versions from step down chopper. Also, we are going to look into the various control strategies used to control the chopper. For further reading, we can follow this textbook on this corresponding page numbers. Based on the relationship between the input voltage and the load voltage V0, the choppers can be classified into three different categories. That is, when the output voltage V0, if it is always less than or equal to the input voltage Vin, then we call such chopper as step down chopper. If the output voltage V0, if it is always greater than or equal to the input voltage Vin, then we call such choppers as step up chopper. Step up down chopper is the combination of these two. That is, for some values of duty cycle, output voltage will be greater than the input voltage Vin. For some other values of duty cycle, output voltage V0 will be less than the input voltage Vin. So, this is the combination of these two. And here we have seen this circuit diagram already in the previous video. It has a switch, an inductor, a diode and a capacitor. This circuit is what we call it as the practical step-down chopper circuit. The capacitor is used in this circuit in order to reduce the ripple content in this output voltage, and this inductor is used in this circuit in order to reduce the ripple current in the load current, and this diode is used in this circuit in order to discharge the energy stored in the inductor whenever this switch is in off condition. So, these three elements, that is the switch, diode and inductor, plays an important role in deriving the step up and step up down chopper from the step down chopper version. By properly placing all these three elements, that is the switch, diode and the inductor, by properly placing all these three elements in the suitable area, I can derive step up chopper and step up down chopper from this step down chopper. If you look at, I have named these three elements. Element 1 is switch, element 2 is diode and element 3 is inductor. I am going to rotate all these three elements in this direction one step, which means I am going to make 1 here, 2 here and 3 here. So I am going to put all these three interchange by one step. So if I do that, I will get a switch here, because 1 is the switch, I will get a switch here, and I will get a diode here, and I will get a diode here, and I will get an inductor here. So this version is what we call it as step up chopper, which is easily derived from this step down chopper. Similarly, step up down chopper can also be derived easily from this step down chopper. Let us see how we can do it. You can just, this switch 1 is left as it is in the same place. But I am going to replace this inductor and diode. So I am going to put inductor here. These two are going to replace, and I put a diode in the reverse direction. This is the change that is needed to derive this step up down chopper. So this is an inductor and this is the diode. So now this becomes the step up down chopper. So from the step down chopper, I derived step up chopper and step up down chopper by just replacing or interchanging the three elements, switch, diode and the inductor. Before understanding the detailed operation of all these three choppers, let us try to understand analytically by using the relationship between the input voltage and the output voltage with the help of duty cycle. We have derived the expression for step down chopper. The relationship between output voltage and input voltage is output voltage is equals to D times the input voltage Vin, where this D is called as duty cycle. This duty cycle is written as duty cycle. This duty cycle is given by T on by T, where this T is equal to T on plus T off. So this is the important expression which we have derived from the previous video. Now this is the relationship between the output voltage and the input voltage for a step down chopper. Similarly, we can derive an expression between output and input voltage for a step-up chopper. Anyhow, I am going to derive it in detail in the next videos. Let us try to look into the final expression of that derivation. V out is equals to V in divided by 1 minus D. So this is the relationship between input voltage and output voltage of a step-up chopper. If you look at, already we have seen that the duty cycle will have a range of 0 to 1. The duty cycle range will be always from 0 to 1. Let us assume that my duty cycle is equal to 0. If I put duty cycle is equal to 0 in this expression, output voltage V0 will be equal to V in by 1 minus 0 becomes 1. So V out is equal to V in. That is when duty cycle D is equals to 0. When duty cycle D is equals to 1, what will happen? V out is equals to V in divided by 1 minus 1. 1 minus 1 becomes 0. So the denominator becomes 0. Once the denominator becomes 0, the output voltage will become infinite theoretically. So theoretically, by varying the duty cycle from 0 to 1, it is possible for me to vary the load voltage from V into infinity. Similarly, let us look into the expression for output voltage of an step up down chopper. As I told that it is the combination of step up and step down chopper. V out is equals to V in into this D divided by 1 minus D of step up chopper. So D divided by 1 minus D. So this is the expression for the output voltage of a step up down chopper. Now let us try to take the values of D from 0 to 1. So let us try to take these values. So when I substitute D is equals to 0 in this expression, I will get V0 is equals to V in into 0 by 1 minus 0. So numerator is 0, denominator is 1. So V in into 0 becomes 0. So output voltage becomes 0. When I put D is equals to 1 in this expression, I will get V0 is equals to V in into 1 divided by 1 minus 1 becomes 0. So denominator becomes 0. So the V0 becomes infinity. When I substitute D is equals to 0.5. When I substitute D is equals to 0.5, I will get V0 is equals to V in into 0.5 divided by 1 minus 0.5. 1 minus 0.5 is 0.5. So this 0.5 and 0.5 will get cancelled. So V0 becomes V in then. So since 0.5 and 0.5 get cancels, V0 is equals to V in. If you look at when the duty cycle is varied from 0 to 0.5, the load voltage will vary from 0 to V in, which means that it is now behaving as a step down chopper. When the duty cycle is varied from 0.5 to 1, the output voltage is varied from V into infinity. So now this is behaving as step up chopper. So by properly varying the duty cycles, it is possible for me to get a voltage ranging from 0 to infinity in the case of step up down chopper. So if you look at these three expressions, that is V0 is equals to D into V in, and V0 is equals to V in divided by 1 minus D, and V0 is equals to V in into D minus 1 minus D, D by 1 minus D. All these three expressions are very, very important. Anyhow, we will try to derive all these expressions and the elemental operation of all these circuits in detail in the next videos. But before going to those operations very clearly, let us try to understand how to control this duty cycle D, which is very, very important to find or to vary the output voltage. So control strategies of a chopper. Chopper control strategies in the sense it is nothing but to control the duty cycle. As I already know that duty cycle is T on by T, where this T is T on plus T off. So duty cycle can be varied or can be controlled either by varying the on time of the switch or by varying the off time of the switch, because T is equal to T on plus T off. So either by varying this T on or by varying this T off, I can vary the duty cycle. So duty cycle is the primary element in all the three versions to get a variable voltage across the load. Controlling the duty cycle can be done in two different ways. One is what we call it as time ratio control, which is also called as TRC, and other one is the current limit control, which is also called as CLC. This time limit control or time ratio control is again classified into two different categories. One is constant frequency system, other one is variable frequency system. Constant frequency system waveforms are given here. Here there are two waveforms. One is for duty cycle is equals to 30% and another one is for duty cycle is equals to 60%. So there are two waveforms. This is for all the three. I have given three different classifications. For all the three I have drawn two waveforms. One is for duty cycle is equals to 30% and other one is for duty cycle is equals to 60%. If you look at this constant frequency system, if you look at the time period of both these waveforms, that is for duty cycle 30% and duty cycle 60%, time period remains constant. Meaning is time period in the sense after the point where the waveform repeats itself. If you look at this waveform, from this point forward, the same waveform is getting repeated. So this is the time period of this particular waveform. Whereas if you look at the second waveform, again this part of the waveform is repeated. So this is the time period of the second waveform. We know that frequency of the waveform is equal to 1 by t. Since the frequency is fixed in both these cases, this is called as constant frequency system. So since the frequency is fixed in both the cases, we call it as a constant frequency system. But if you look at the on time here is very less. Whereas here if you look at on time is larger when compared with this. Off time here it is larger, off time here it is very less. So that is why duty cycle is varied. But still the duty cycle is varied, the frequency remains constant. That is why this system is called as constant frequency system. And the next one is the variable frequency system. In variable frequency system, we have two other classifications. One is with constant on time, other one is with constant off time. Here if you look at the frequency is not constant. How do I say that? If you look at the first waveform, the duration of this waveform is till this point. From this point only the waveform started repeating again. If you look at this part is going to repeat again. So the time period of the first waveform is this point. Whereas if you look at the time period of the second waveform, this repeats after this point. If you look at this part is getting repeated. So here time period is different. If time period is different, frequency will also be different. That is why this is called as variable frequency system. But again, duty cycle can be controlled either in two ways. Here if you look at the on time, in this case and in this case is remaining same. This duration and this duration is same. But whereas off time is so large here, whereas off time is very small here. Even though the on time duration is same, off time duration is different. That is why this comes under D is equals to 30% and this comes under D is equals to 60% duty cycle. So if you look at in these two cases, on time remains constant. So that is why this is called as constant on time system. Here if you look at constant off time, if you look at the frequency is again different in these two cases, but off time of the switch is maintained constant. Here this is the off time, this is the same off time, same duration. But on time if you look at this is very small, whereas on time is very large here. So that is why this comes under constant off time system. Now the last one is the current limit control. Since we have an inductor in the system, I can maintain the duty cycle, I can vary the duty cycle based on the inductor current. Once the switch is on, let us assume that once the switch is on, the inductor current increases. Inductor current increases, I make the switch on. I turn on the switch, inductor current increases. So once it has reached some maximum value, what I will do, I will turn off the switch. Once I turn off the switch, inductor current will slowly come down. Once it has reached its some minimum value, again I will turn on the switch. So based on the value of current, I can, once it has reached some minimum value, I will turn on. Once it has reached some maximum value, I will turn off. So turn on and turn off of the switch is based on the current through the inductor or current through the load. So this on time and off time is based on the current. That is why it is called as current limit control. So these are all the various control strategies available in the chopper control, which is what we call it as duty cycle control. This constant frequency system is also called as pulse width modulation control, PWM control. This variable frequency system is also called as frequency modulation control. So these two has the names of PWM, that is pulse width modulation control, and frequency modulation control. There are lot of advantages in this PWM control when compared with the frequency modulation control. Let us see what are all the advantages of PWM control over the frequency modulation control, variable frequency control. So if you look at the design of L value and C value, that is inductor design and capacitor design, will be very easy only if the frequency is fixed. When the frequency is variable, designing the values of L and C is very complex. So in that cases, in most of the cases, that is why this PWM control or constant frequency system is used, because to design the values of L and C, if the frequency is fixed, that becomes easy for the designer. The second important point is, since the variable frequency system, the frequency is varied, there may be a possibility of interference with signaling and telephone lines in the frequency modulation technique, which will unnecessarily create disturbance in the both telephone lines as well as in the power circuit of the chopper. So we have to avoid this variable frequency system. And the third drawback of this variable frequency system is, when the off time is so larger, something like this, then the chances of current may come to zero and it may stay in zero for some time, which means discontinuous conduction mode of operation may occur if T off is very large. So this T off is very large in the case of constant T on system in many cases. So this is another problem which will lead to discontinuous conduction mode in the case of variable frequency system. So these three advantages of constant frequency system makes it more superior when compared with variable frequency system, and this system is used in many of the choppers are concerned. And whenever I require a current limit to be done in a circuit, this current limit control can be used. But this requires an additional sensor to sense the current. So these are all the various types of control strategies that is used in choppers. And in the next videos, we will try to go into a detailed understanding of all the three types of choppers with various types of operating waveforms. Thank you for your patient listening. Thank you.